In this question, we're asked to use integration by substitution to find this particular integral. You'll notice that it's a definite integral because it has limits. So using substitution, we can let u equal, we have two options. We could possibly let u equal 2x minus 3, or possibly 2x minus 3 to the power of a half. We can try u is equal to 2x minus 3 to the power of a half. Just as a note going forward, if we square both sides, we end up with u squared equals 2x minus 3. And then if we add 3 to both sides, we end up with u squared plus 3 equals 2x. And then if we divide both sides by 2, we'll end up with u squared plus 3 divided by 2 is equal to x. And we're going to use this fact a little later on in the question. Okay, so once we have our substitution of u, we want to differentiate it with respect to x. And we obtain this using the chain rule. The 2's cancel, and we can see that this is a reciprocal because there's a negative to the half power there. So we can rewrite this as du dx equals this fraction, noting that this is equivalent to our original substitution of u. So we're going to use this fact. We can almost imagine eliminating that middle section and just thinking about these two endpoints. And what we want to try to do with integration by substitution is collect all the u terms on one side of the equal sign and all of the x terms on the other side of the equal sign. So if we do that, we'll end up with u du is equivalent to dx. And again, we're going to use this a bit later on in our substitution. Following on from that, what we can do is we can begin to rewrite our original integration in terms of u. So we know that x in terms of u is this, something that we derived a bit earlier on. So we're going to put that in its place, which is what we have here. And then we have 2x minus 3 to the power of half. Well, we know that is just u. So that's u there, equal to this. And well, what is dx in terms of du, or in terms of u? We found that earlier on to be dx is equivalent to u du, so that's that part there. And they're all multiplying each other. You'll have also noted that we've had to convert our x values into u values. Well, how do we do that? What we can do is we can think about when x is equal to 2 for our bottom limit, we can substitute that into our u equation, and we end up with a value of 1. And similarly for our upper limit of 7 over 2, if we substitute that into our u equation, we end up with an answer of 2. When you get better practiced at this, you'll often not bother doing this kind of working. You may just go straight into a table configuration like this to summarize the same information. And this is just saying when x equals 2, u equals 1. And when x equals 7 over 2, u equals 2. So these are our new limits as we've moved from x to u. And you'll notice x equals 2, u equals 1. X equals 7 over 2, u equals 2. So we've done the conversion there. And what we want to do now is try to simplify this. Well, we notice that there is a constant fraction here of a half, which we can extract out of the integration sign. Now, if we do that, we'll notice that we get u squared times u squared gives us u to the power of 4, and we get 3 times u squared, which gives us the plus 3u squared du. So I've dropped the u equals 2 and the u equals 1 because we're integrating with respect to u, so we assume that is u equals 2, u equals 1. Okay, so if we carry on and start the integration with respect to u, this becomes u to the power of 5 over 5 plus u to the power of 3. The half still remains outside, and we have our limits in terms of u, 2 and 1. So now we can try to evaluate this integration using those limits. And substituting all those values in, we find that we get an answer, finally, of 33 over 5. The units squared is simply a technicality just because we have to remember that whenever we're integrating a function between limits, as we are in this case, we are actually working out the area underneath the function between those two limits.